Good day, we are Stephanny Frasser, Manuela Lopez, and Maria Paz Galindo, and we are going to present you our practice 5, which name is diffusivity of a mosquito repellent.
Mosquito repellents are volatile chemical substances that due to their scent or composition, it can be used as a barrier, providing protection against insect bites. They are important as they prevent disease caused by mosquitoes such as Zika and dengue. The effectiveness of repellents is determined by their diffusion coefficient. The diffusion coefficient is a measure of how quickly a product diffuses in a medium. It can be used as an indicator of the repellent release rate, which depends on the vapor pressure at room temperature and it is related to the boiling point of repellents. Diffusion coefficients and the repellent release rate are temperature dependent, as it is a measure of the average velocity of molecules. Consequently, diffusion is higher at higher temperatures. The objective of the practice is develop a protocol to determine the effect of temperature on the diffusivity of a mosquito repellent. In the laboratory, we follow the following methodology. After defining the water temperature at 10 degrees Celsius, a glass container was selected and marked to which 100 milliliters of water with the selected temperature was added. Subsequently, using a ruler, a distance of 3 centimeters from the base of the container was defined to take the samples. Next, dye was added to the repellent. Continuing the process, using a pipette, 10 milliliters of repellent with dye was added to the glass container. Afterward, samples of the mosquito repellent water solution were collected at the selected distance every minute for 4 minutes. Then an analysis of each sample was performed using a UVB spectrophotometer with the objective of measure absorbance in the UVB region and determine the concentration. This procedure was repeated at three different temperatures 30, 60, and 90 degrees Celsius.
To find the diffusivity coefficient, it was first necessary to find the concentrations using the Beer-Lambert equation. In this, we use the molar extinction coefficient of acetic acid in methanol for each wavelength at which the maximum absorbance occurred. For this, we plotted absorbance versus wavelength graph that will be seen below. After finding the concentrations with the help of simplified sort equation, the diffusive coefficient was found for each temperature. Here we can see the graph that we use for find the epsilons for acetic acid in methanol. Here we can see the graph of absorbance versus wavelength for the temperatures of 10 Celsius degree and 30 Celsius degree. In the 10 Celsius degree graph, we can see that for the four times, the maximum absorbance was between the 500 and 550 wavelengths. For the 30 Celsius degree, we can see that the maximum absorbance for the times in 1 minute, 2 minutes, and 4 minutes was between 400 and 450 wavelength, and for the time of 3 minutes was between 500 and 550 uh, for the wavelength. Here we can see the graph for absorbance versus wavelength for the temperature of 60 Celsius degrees and 80 Celsius degrees. For the temperature of 60 Celsius degrees, we can see that for the times for 1 minute, 2 minutes, and 3 minutes, the maximum absorbance was between 500 and 550 wavelength, and for the time of 4 minutes was between 600 and 650 wavelength. And for the graph of 90 Celsius degrees, we can see that for the times of 4 minutes, 2 minutes, and 1 minute, it was also the maximum absorbance between 500 and 550 nanometers of wavelength, and for the time of 3 minutes was between 700 and 750 nanometers of wavelength. The simplification of the third equation may increase the error in the calculation of the diffusive coefficient, since different assumptions are made. The first is that the system is in a steady state, so the term involving the velocity is cancelled. Likewise, it is assumed that the container has the same temperature in its extension, so that is not temperature gradient, and the term involving the thermal diffusivity is cancelled. This leads to an equation where the diffusivity will be in terms of the change in concentration over both time and distance. However, it is known that the diffusivity also varies with varying temperature. On the other hand, fixed law cannot be implemented for the determination of the diffusive coefficient in practice, since it is necessary to know the value of of the mass flux. And this depends on the average displacement velocity of the molecules, which is very difficult to determine from the methodology used. According to the theory, it is expected that the temperature has a direct relationship with the diffusivity. This means it increases with increasing temperature because the molecules move faster, so the average collision path increases, thus generating that these diffuse at a higher speed. However, in practice, we did not obtain results that agreed with the theory, so there may have been errors in the data collection as well as errors induced by the choice of an epsilon that correspond to a compound other than the one that composed the majority of the repellent. In addition, micelles were observed when the repellent was added to the water, which means that a null phase with hydrophobic compounds was present in the repellent, which explains why the diffusivity values obtained have a very low magnitude. This means that it's very difficult and slow the diffusion of repellent in the medium water. Finally, the diffusivity is affected by the molecular composition of the compounds, since among many factors it depends on the particle size, as that means that the larger the particle size is, the more difficult it would be for the compound to diffuse. On the other hand, the presence of interactions between the solid and solvent molecules can generate changes in diffusivity. This implies that if van der Waals interactions exist between the molecules to be diffused and the molecules of the medium, it will be more difficult for them to diffuse. In the graph, we can see that the coefficient is constant in respect of concentration, but varies respect to temperature.
Finally, we are going to present you our conclusions. The first one is that the objective to develop a protocol to determine the effect of temperature on the diffusivity of a mosquito repellent was partially achieved. This considering that the Soret approximation method did not yield results that demonstrate the correct behavior of thermal diffusivity. That is, that the higher the temperature, the higher the diffusivity should be. This is possibly due to the interactions generated between the oily and aqueous present in the repellent. And our second conclusion is that the highest absorbance at all temperatures used was at a wavelength of 534.97025 nanometers. And finally, for future research, it is recommended to look for a repellent with a single phase or to look for a method to find the diffusivity that is effective in this type of repellent. In case of using the same method, it is necessary to use the molar extinction coefficient of the correct solvent and make a detailed research for it.